Okay. So this is the last chapter, quantized energy levels in atoms. In the photoelectric effect, you imagine the electrons will pick up some energy, a packet of energy, and if that energy is enough, it will break the bond to the metal, and then the electron will fly off with some kinetic energy. Okay? So this is not a thing. That is not a thing that is about energy levels. That's not something that we describe electrons as having an energy level. Okay? When they're flying off, they just have some kinetic energy because you broke them free. Okay? But you don't, to break the electron free of the metal is actually just one thing you can do. The thing that you can do before that is that you can actually get that electron to jump up in energy states, all right? So there are all these different levels for all of the electrons on a particular atom where if you give them the right amount of energy, in other words, the right frequency photon of light, you can get the electron to inhabit a higher orbital for an instant before it drops back down again. So what you imagine is the electron absorbs a photon of light that is exactly correct, in other words, exactly the right energy difference between two of its many levels, okay? And what it'll do is it'll absorb it, jump up for an instant, and then jump back down again and give off that packet of light exactly the way it got it. And so the light will be emitted back out again at the same energy that was taken in. That's the most basic version of what's going on, right? Okay, so Niels Bohr proposed a simple model of the atom in the 20th century. He suggested that the electrons were in like circular orbits around the positive nucleus, but that the orbits could only be certain sizes. Now, this is where they needed a quantized version of a model, because if the electron could occupy any orbit around the atom, then the range of frequencies that you could use would be continuous. Like, it'd be any frequency. You just get the electron to be a little bit further out, right? But it doesn't work that way, of course, because the universe can never be too simple. The levels that it can occupy are very specific. Not only are they very specific, they're specific to the element, which means every element has its electrons exhibit a different set of energy levels. That's how we know that the sun is made of hydrogen, that there's neon in the universe, that there's water over there, in some cloud. Because what we do is we take in the light coming off those elements in space and we analyze it. We look at it and we say, oh, we've got a certain pattern of spectral lines of these photons that are coming out of that cloud. What do they match up to? Well, you go to the lab and you go, well, in the lab, when I energize like hydrogen and helium and neon and all of those things, I take a reading of what those energy levels are, the photons of light coming off of those electrons for each of those elements. So I have myself a nice little key. I'm like, oh, okay, so hydrogen looks like this. So when I get light from space that lines up exactly the same as hydrogen, I know I'm looking at hydrogen, all right? So you don't have to guess. It's not some weird kind of, hypothesis that the sun might be made of hydrogens. No, it is. Because it shows up exactly in experiments, all right? Wait. Now, this is the other idea. You don't imagine that the electron is moving around in a wave pattern. That's not what you're supposed to imagine, okay? What you're supposed to imagine is that the electron itself is a wave, okay? So it's exhibiting its de Broglie wavelength, okay, because it's matter, so it'll have a de Broglie wavelength and a velocity and a mass and all of that, right? But you don't imagine it as like a little ball moving around in a wave pattern. You imagine it as though the wave is the electron. You've just taken the electron and spread it out into a line, and it's set up a standing wave. So the standing wave is when you know that the electron is in a particular energy level, okay? So that's the important distinction there. So the model for the atom that Rutherford proposed in 1911, the atom consisted of a small, dense, positively charged nucleus surrounded by a cloud of electrons, has a weakness because the accelerating electrons should radiate energy and spiral into the nucleus. In 1913, Bohr said that the electrons should not be considered to be orbiting like planets, because that wasn't really accurate. Didn't explain what they saw. he said that they simply existed outside the nucleus with certain amounts of energy. According to Bohr, the electrons in the atom existed in certain discrete energy levels, which is what we deal with here. It might sound a little bit complicated, but as soon as you see what you actually have to do, it's not that bad. Okay? So, each element has certain allowed energy levels that are unique to that element. That's what I said earlier, how we know the periodic table of elements. They all have their own signatures. When you get a mercury vapor lamp or a sodium vapor lamp out of the back room there and switch on, it makes all that light. All of that light is coming from atoms which are all the same element, so they'll all have their own. In the visible spectrum, you see they'll maybe fluoresce kind of bluish or purplish, because that's the part of the light that's coming off that you can see. But there's a whole range of frequencies coming off there that you can't see, that are off both sides of the visible spectrum, right? So there's this really unique fingerprint for every atom. So what's happening is energy is hitting the vapor inside the lamp. It's energizing the electrons. The electrons are sucking in the energy appropriate to the energy levels of the atoms in there. All those atoms are the same, so they're all doing the same thing. They are then emitting light at very specific frequencies, and that's why that light kind of looks a bit funky, a little different to normal light, because it's not everything. It's just very specific to that element, okay? So that's what's happening. That's sort of like a hot gas emission is what it is, and that's part of this, all right? So electrons can only exist in one of these allowable energy levels, not in between. Energy levels are quantized. Okay, now these become points that are very nice and neat when they try to get you to explain why electrons can only inhabit, and you're like, oh, no worries, I got this. It's like, yeah, they can only exist at specific energy levels. They set up standing waves at each level. They must absorb a photon in its entirety. To move that photon has to be of the appropriate frequency. That's how you explain, in those explain questions. All right. So if an electron is given extra energy, it can move up to a higher energy level by absorbing an amount of energy equal to the difference between the energy levels. And you'll see a diagram in a sec where it shows what the levels actually look like. All right. When an electron is at a higher energy level, when an electron in a higher energy level returns to its normal ground state, where it's meant to be, it emits the energy in the form of a photon. You can't always see that photon, depends on what kind of light it is. The energy of the photon equals hf, as usual, all right, is equal to the difference in energy levels that the electron moves between, all right? So how does that make any sense? Let's have a look at an energy level diagram. Here we go, here's a typical energy level diagram. This is for hydrogen, and it's not all of the hydrogen lines. It's just a few of them to show basically what's going on. So in the ground state, the electrons can inhabit, they'd be at this level here, all right? So when an electron, let's say, okay, how's this diagram? All right, so the ionization energy is 3 points. Okay, let's go to the ionization level. Ionization level, if an electron in the ground state absorbs 13.6 electron volts or more of energy, then you rip it off. Ionization means you've lost the electron. So if you've done any chemistry, you know when you lose an electron, you create an ion. Yeah? So that's why they call it that. So it's the ionization energy. In other words, when the atom becomes charged once it's lost one of its electrons. Okay? So if you hit an electron in the ground state of 13.6 or more, it will leave the metal and its ion is gone, okay? But if you hit it with an energy that is less than that, all right, but that energy equates to either the energy level gap between here and here, okay? So an electron in the ground state can jump up to that level if you hit it with a frequency that is equal to that energy, okay? It will inhabit that spot for a little bit and drop right back down again and give you that photon back again. It can't give you any other photon. It can't give you anything in between that gap because there is no energy level in between that gap. So, for example, if I get an electron to jump up to this state by giving it a photon of the appropriate amount of energy between here and here, then one of two things can happen. Actually, three things can happen. The first two are, it could drop back down again an instant later and give me back exactly that photon that I gave it, right? Or it could drop down to this level, giving me a little photon of this energy level, because there is an energy level here, all right? And then when it occupies this state for an instant, it might drop down again and then give me another packet of energy equal to this energy level. So I can energize the electron up here, it can come straight back down, or it can step down, okay? Giving you what would essentially be the sum of the original energy that you gave it. And there's no losses, all right? There are no in-betweens. It either happens or it doesn't. And I did hear, and I don't know if this is true, because then I heard later on that's like, oh, this isn't really what happens. But I remember them saying that because this is not a continuous thing, this is discrete, technically you can imagine the electron disappears from the spot that it's in and reappears. It's never in between, because there is no energy in between. So it's kind of a weird little spooky thing, which I don't know if that's actually true, but well, yeah, so it's kind of like teleporting between levels is one thing that I've heard, but I don't know if that's actually totally accurate. Every time one scientist says something, another one goes, oh, well, no, not really. And you know, who do you believe, right? Anyway, okay. So in here, there's a couple of things that you have to keep in mind. If an electron is moving up, you have to draw an arrow that goes up, all right? If an electron is coming down, so if they say electron has absorbed energy and it moves from level 2 to level 4 or something, or level 1 to level 5, then you have to draw a line that shows level 1 to level 5. Like, this is how simple it can be. You can't draw an arrow going the wrong way, because it's said in the question, absorb. The electron's going up, not coming down, all right? So you draw the arrow the wrong way, you've got it wrong. Okay, you don't get the mark, okay? Then if it says, oh, an electron from the state 5, or in the 5th energy level, comes up, what are all the possible photons that you can get out of it? Okay, so you go, oh, okay, well, it can drop straight back down. So that's coming down. The arrows go down. I mean, it's a simple thing, but I just make sure that it's clear so you don't, miss out on easy marks by putting the arrows the wrong way. Spare a thought, is it absorbing or is it emitting? Okay, that's important, all right? It can come directly down, giving you that full energy in one photon. Or it could come down to here, right? Or it could come down to here and here. But of course, you've got all of the other energy levels as well. So there's the transition from here to here. There's the transition from here to here. Okay, and have I got one from here to here? There. And then obviously, sort of one of the last ones down here. So one typical question is, how many different photons could you get from an electron inhabiting the 5th state? So you go, oh yeah, 1, 2, 3, 4, 5, 6, 7. As many as you can find, trying really hard not to miss one. Really easy. Now, of course, that doesn't count ionization, because ionization, the electron's gone, okay? So we say that the energy, that the atom is excited because of its electrons, okay? It's not that the electrons are excited, the atom is excited because its electrons have been raised from the ground state up to some other level, all right? Yeah. Good question. I asked this question, and for a while, we wondered, oh no, you can't do that. You can't, for example, can an electron go the other way, absorb, and then while it's in that position, all right, while it's in that state, before it gets a chance to come back down again, it got hit by another photon of the next energy level. Can it then bounce up from this level to this level and then start coming down again? Well, apparently, after doing some further reading, yeah, yes, it's possible to do that, okay? So electrons can stage up if, in the event that electron was hit by the right photon, while it was in that thing. But you imagine there are billions and trillions of photons. It would happen once in a while. Imagine your light is coming off the sun, right? So the light's coming off, so the sun produces the full spectrum of light, all of the wavelengths, okay, in its processes of making its energy. It fuses 4 hydrogen atoms together, makes a helium atom. That helium atom is now 4 times heavier than every other atom in the sun, and it sinks to the center, right? Where you end up with a big pool of helium right in the middle, getting hotter and hotter and hotter, okay? At some point, that helium starts to fuse and makes the next element up, and it keeps going. It goes up to about iron. Now, when you get to iron, apparently, again, I'm not a scientist, but I've read, once you get to iron and try to get past iron, the fusion process consumes energy, doesn't give it off anymore. And that makes a limit to how many elements the sun can make, right? So where do the rest of the elements come from up to uranium? Well, when the sun dies. When the sun dies, there's a huge injection of energy, and all of a sudden, up to uranium, everything else gets flung out. But of course, it kind of explains why some elements are incredibly common in the universe and others are much more rare, okay? Because obviously it's much harder to make the heavier ones, right? So that's basically what's happening. Now, the process of fusion gives you white light coming off the sun. Yet, when you look at the sun, you see emission spectra. You see spectral lines in the hydrogen. The fingerprint that you see is hydrogen. You're like, well, how come? Well, when you look at the sun, it's creating its white light. It's going up. It tries to pass the corona, and the corona is a cloud of hydrogen. So as it goes through the hydrogen cloud, what it does is the hydrogen cloud redirects specific wavelengths that are specific to hydrogen because it's only hydrogen in that cloud. So it absorbs certain frequencies and then immediately emits them again, right? The thing is, the way we imagine it is those emissions are in all sorts of different directions. And so what it means is when you look at the light from the sun, what you get is a deficiency in photons in specific areas that have been redirected as they went through the cloud of the corona, all right? And so you see the emission spectra, even though the sun is producing the full spectrum, it gets interfered with as it leaves and comes off and spends that 8 minutes getting here, all right? So that explains the absorption spectra, why you see gaps in the spectrum when you're looking at white light going through a particular element, all right? Absorption. Emission is a little bit different. Emission is when you only have one type of element, you energize it, and the only energy that that element can actually take is specific to that element. For example, the sodium lamps, mercury lamps, they're only one type of atom in there, so they will only emit those in those really specific frequencies. So that's the difference really between absorption and emission. In absorption, you're starting with white light, but you're redirecting specific frequencies, so you get gaps. In emission, you only have one kind of atom, which means you can only have one set of spectral lines, okay? All right, now, please, and I did this myself like a week ago, where I'm like, oh, yes, the bigger wavelength, more energy. No, bigger doesn't mean more. Okay, just be very, very careful. Don't trap yourself with that whole, oh, greater wavelength, oh yeah, more energy. It's the exact opposite. Just keep reminding yourself, okay? All right, so higher frequency is more energy, not bigger wavelength. Just repeat that 1,000,000 times. De Broglie's explanation of energy levels. And this is the last bit, okay? De Broglie's explanation for energy levels comes into play as if you imagine the electron is inhabiting like a standing wave around the atom, then what you have to think to explain the next energy level, you'd have to imagine that the photon of light comes in, it must have a wavelength that matches this, because obviously, to set up a standing wave, this is a fixed number of wavelengths around the atom, okay? And they all have to fit. You can't have like 3 and a bit waves around the atom, or 4.5 bits, or they have to actually fit around the atom. So the way we imagine it is that the wave that comes in, you've got 1, 2, 3, 4, 5. 5 clear wavelengths. So the wave to come in to make this atom or electron jump to the next energy level has to, you imagine breaking this, spreading it out and adding an extra wavelength that has to fit with the others. And that was de Broglie's explanation on why there were specific energy levels. All right? They all have to sort of line up. Obviously, it's more complicated than that. There's way more maths in it than we actually go through in high school physics. But as far as you're concerned at this point, the wave has to be appropriate to continue the standing wave. Otherwise, if it's not, it tries, it wobbles, and goes, well, you're not right, and nothing happens. So the electron essentially ignores, it'll ignore any wave packet that is not of the appropriate energy because it can't incorporate it into the existing wave that it's in, all right? And like I said, every element has its own set of these, okay? So the only other, so let's have a look at this. Down here, this is the only, not a lot of maths involved in this. You've got here the circumference, okay? So the circumference of the orbit, okay? So the circumference of the orbit, 2 pi r, okay, is equal to a whole number of lambdas, all right? Okay, so where's that lambda? Where did we get that lambda? Well, that's de Broglie's wavelength. Lambda equals h on mv. So with this combination, you can work out a whole bunch of things. You can work out the radius of the orbit. You can work out what the wavelength is, and with that, you can figure out, any of these values that are unknown, you can figure out by aligning the appropriate formulas, okay? So some of those appropriate formulas, I just got them prepared earlier. 2 pi r is equal to h over mv, okay? So, yeah, 2 pi r is equal to h over mv, and then the last one is mvr is equal to nh over 2 pi. So sometimes they give you, they say, oh, we find a photon of this energy, or this wavelength, okay, at the atom. And then they show you the diagram of the energy levels of that particular element. And then they say, well, how many possible photons can you get out of this as it comes down? And what you do, well, what sometimes students do is they ignore the energy that they use because they stated it in the question, right? They stated in the question, but you've ignored it as a student and you've just gone and counted every energy level without realizing that the photon didn't get you to the top energy level in the first place. It only got you to like the second top or third top, which means you don't have the possibility of getting all of them because the electron never got there, never got to the top, all right? A standard booby-trapped question, okay, that they will throw at you occasionally, all right? So yes, all those levels are possible if you had given the electron enough energy to do them, but you didn't, again, and then you get the question wrong, all right? Okay, now if we look at this, you'll often find the energy levels are given in electron volts because they're just so much easier to work with, all right? And kind of like, I know when you introduce electron volts, everyone goes, oh, why do we need a new bloody, version for? It's just joules is good enough. The joules are so ugly comparative to this because, you've got real numbers. You can do these in your head, all right? So let's see. Which one or more of the following photon energies can be emitted by a mercury atom which is initially in the second excited state? Ground, first, second. So the electron is in that state. So which one or more of the following photon energies can you get from an electron that comes down from there? So you could get that one. So an electron is 6.7 electron volts, okay? You could get this one, which is the difference between them, and you can get this one. And you'll notice not all of them will be here, okay? So they don't have to list every possibility, from the question that is possible. So you go through, is 4.9 there? Well, yes. And what's the difference? Come on, quick maths, you know you can't trust me with it. 1.8, beautiful, 1.8. So you'd go through, it's like, yep, they're the possible out of what is given, all right? There is obviously one more possible, but they didn't list it, so it's not part of the answer, all right? Yeah, it's that hard, okay?
So what if you said a photon that's not one of those?
then what happens when you send a photon that is not one of those energies, it may try to be incorporated by the electron. The electron can't set up its standing wave. It's just this wobbly thing that collapses and just goes, nah, and the photon will go through. So there are other questions. The photon will go through and just not really interact with anything. It's just not right, and it knows it. So,
There must be in mind there. Because it doesn't get it much exactly.
well, the model doesn't really allow for it not being perfect. Again, but that's the limit of the course. You don't need to worry about again, they never really make you worry about the reality of the situation. It's just like, this is what you need to know, because when you go tomorrow to study somewhere else and you've got a lot more information, a lot more mathematics, yes, okay, all of a sudden all those cool little things, details start to come out, you know. But at this level, let's just get your head around how it works, so you don't turn up to university with nothing, you know what I mean? So, all right, okay. Oh, last thing. Sometimes they will ask you to draw an orbit of a specific number of wavelengths. I know, it looks really hard, but it's actually really easy. You imagine a circle, right? And if it says, draw an orbit of 3 complete wavelengths, now they don't care if they're perfect. They just want to know that you know what it is. So if it's 3, it's 6 crossing points. That's it. Just follow that. If it's 4 wavelengths, it's 8 crossing points. In other words, if I'm going to do 3 complete wavelengths, I'll go 1, 2, 3, 4, 5, 6. I know they're my crossing points. And now I just hit them when I draw my wobble. That's as neat and as good as it needs to be. So I go like that. Bam. Now, is that all you need to do? Well, I think that's all you need to do normally, yes. But if you want to show that it's a standing wave, you know, kind of like not having too much of this in the way, you can then go, okay, dot in like the standing wave version. You know what standing waves look like. What the hell did I do there?
Yeah.
That's all right. It's close enough. Yeah, it's ugly, it's hideous, but it's correct. Doesn't matter. That's enough to get the mark out of it. So how many wavelengths? If you look at the original question, how many wavelengths is this one? Well, there are 1, 2, 3, 4 crossing points. It's 2 wavelengths. That's all. All right. So it's pretty much as hard as the topic gets. So, in this case, what's the question? Which one of the following represents a standing wave state electron hydrogen circumference is equal to 4 wavelengths? Yeah, you've got to find something that's got 8 crossing points. 1, 2, 3, 4, 5, 6, 7, 8. Yep, that's the one. It's that easy, all right? So never worry about how hideous your thing is. Okay, let's have a quick look at example 4 just to show you, again, give you an idea of the sorts of things they can ask. Which one of the following transitions on the energy level diagram demonstrates the change in atomic energy levels for the emission of a photon of energy 1.65 electron volts? Now, it's emission. Which way does the arrow go? Down, okay? Has to go down. Do arrows ever finish in midair? No. Okay. They are clearly not it. There's only one arrow. You don't even have to calculate it. This one's going the wrong way. It's emission, it's coming down. It has to be A or nothing. All right. So, yeah. Okay?
It's not 1.65.
Oh, it better be, because if it's not, then...
1.61.
So
1.65 it's meant to be.
1.51.
yeah,
Is it?
I checked that as well. Because I only meant to like find the difference and like minus.
Yeah, the difference is 1.51.
Which one? Part of the emission spectra is shown produces a photon. A sodium vapor balloon produces a photon 1.65 electron volts. Which one of the following transitions on the diagram?
So it's like the top.
So it's like 3.6.
Oh, no, no,
3.75.
yeah.
3.75 or 2.1.
Oh, I just done like
Yeah, you minus, you subtract them. Yeah, that's all it is. You just subtract them. Okay? All right. I don't know, is there anything else in here that needs any further explanation. Have a look at here.
Arrow on the right makes it look like it's
That
on
would
the
be
second
100.
one.
Oh, okay. Have a look at this. Now, your sort of provided or starting point. This is your starting point help sheet. Now, I suspect some people don't really read these, okay? And so I'm going to read it with you because I want to point at where these different bits are useful, how you use them, because so many times you bring a help sheet in with you and there's an answer to a question in the SAC and you still got it wrong and it's on the help sheet because you didn't know that that was the answer, all right? It's really important that you know what's on your help sheet and how you're supposed to use it, okay? What's the point of bringing in the answer and just ignoring it? It's sitting right next to you. What I want to do is just really quickly go through wave particle nature of light, why the ring pattern is observed, dot points that explain. Now again, you try to personalize your answer as closely as much as possible from the situation. Sometimes it's not even possible. The question is so basic that a standard written right off your help sheet answer is all they want. But you know, if it's pitched as Melanie is doing an experiment, okay, then put Melanie's name in your answer because then it makes it obvious you didn't just regurgitate exactly word for word what you had on your help sheet. They don't like that. They want to have some semblance of it being real, okay? So don't do that. So the ring pattern is an interference or diffraction pattern formed by the X-rays passing through the metal. The rings themselves represent positions of concern. Notice the language is there exactly out of the text, all right? So you're stating everything, and it's nice and concise, and you use as much of it as you need to explain the question, all right? So that's that. Electrons' de Broglie wavelength compared to X-ray. That's why I put it there. It's common. It turns up on exams. It turns up in SACs. All right, so here is, don't just go in with this having never read, oh, it's there. If I need it, I'll read it then. It'll be right on the day. No, read it before the day, all right? Make sure you get it, okay? Moving electrons and X-rays have very similar wavelengths. As they share similar wavelengths, they will scatter to form similar diffraction patterns. This demonstrates the wave nature of matter. Even though electrons are considered solid pieces of matter, they scatter as though they were behaving in the same way a wave does. All right? So it's very concise. It's explaining exactly what's happening. Okay? Momentum. They will have the same momentum. Of course, don't forget momentum is only ever an SI unit, so you only use 6.63 if you're doing a calculation with it. All the little reminders that I see students do get wrong over and over and over again, they're all right there to make sure that they're in the front of your brain, okay? Energy, if the momentum's the same, the energies are not between the photon and an electron, or the photon and any piece of matter they use. Sometimes they throw in an alpha particle because we say the word electron so many times, they know just saying alpha particles freak you out. Because like, what's that? Who cares what it is? They told you how much mass it has, and they told you how fast it was going. Who gives a crap what it is? If you don't know what an alpha particle is, just go with the maths. MV. Did it give you M? Did it give you V? Whatever. Whatever alpha particle, gamma particle, magenta particle. Call it whatever you like. Just follow the maths, right? All right. Einstein's photoelectric effect. Sometimes you get a question that is like 5 marks, and explain how Einstein's photoelectric effect is used to explain this particular behavior, whereas a wave model just doesn't work. So now it's 5 marks on this question because you are explaining not only why Einstein is correct, or Einstein's model explains the phenomena, but you also have to chuck in a couple of points of why the wave model fails. So it's important to give the whole story, okay? Especially when you see a question 5 or 6 marks and it's all lines. It's like horrific when you see that, right? No one wants to see that, but they do it to you sometimes, okay? They'll throw in 6-mark question, explain. So part of the explanation is not only why this is right, but it's why that's wrong, or why this is right and why that's wrong, okay? So the whole story, okay? We went over, and so that Einstein dot point. What are you doing? What are you doing? Okay. That Einstein dot point starts here, but it completes, and I got it out of answering a question like that. So I saw a question like that in a past exam paper. I thought, wow, who's going to get this, right? There's so many points in there. So I broke it into a dot point answer, which is something that I suggest students do all the time. You find something dodgy like that, something really complex or like that needs a lot of detail, you can just go, oh, what was their answer? Is their answer like really concise and gave you every point? Of course it is. And so you then adapt it for your help sheet. The precious few people actually go to the trouble of doing that, so I did, all right? Like I said, you do need to read them. They need to be in your head, okay? I put them there, but you do need to be kind of familiar. Yo.
Also came back in
What are you reading? Question 7? All right. Wait, is there anything else on this help sheet that I could... Okay, and again, all of the... Like, just to finish off about the help sheet, look, explanation of absorption, explanation of emission, all right? All the different versions. Everything is in there, but you do need to read it carefully and have it all in there. This is a result of another question I saw in an exam. Okay, dot points created out of the ideal solution. All right, so you can do that for the ones that I haven't found or I haven't seen. All right, so yeah.